welcome back. Welcome back and welcome if you are new here. Let's continue talking about limits at infinity. So we've already talked about this with polynomials and constant functions, but now let's practice with rational functions, which just basically means we make a fraction. So we have a numerator and a denominator. Okay, numerator, denominator. And that's it. So basically, let's just work an example. Let's say we have the limit of x squared minus 6 divided by 4x cubed minus 2x plus 7 as x approaches infinity. So now this whole thing is our rational function. This is our f of x now. Okay? So we can apply the same logic that we did for polynomials individually, for the top and the bottom separately, and then we put it together. So basically, when x gets infinitely large, really big, 1 0 0 0 0 0 0 0 0 0 0 0 0, then you square that. That's going to be huge. This minus 6 becomes negligible on the top, right? Same thing here. We have an x cubed times 4. So 1 0 0 0 0 0 0 0 0 0 0 0 to the third power. That's huge. So this plus 7 is not going to matter as much, and neither is this minus 2x, right? Compared to a cubed, this linear term isn't going to do very much when x gets infinitely large. So again, we only care about the leading term, which is the one that has the highest power, the highest degree, the highest exponent, right? So we do that for the top and the bottom separately. So now what we get is we still have this fraction, but now we just have the limit of x squared over 4x cubed. But since x is approaching infinity, we're not worried about the case where x equals 0, so that's okay. We don't break math or anything. We just need to remember our exponent rules. So in that case, our x squared and our x cubed cancel to leave us with just one x left. So we have the limit of x as it approaches infinity of 1 over 4x. Now, you can either at this point pull out the 1/4 and say limit as x approaches infinity for 1 over x equals 0, or you can notice that if x gets really big, you get 1 over 4, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, which is really small. It's still positive, but it's going to approach 0. Okay? So this line of thinking is really just do the numerator, do the denominator, see what the highest degree is, which carries the most weight, and then use your exponent rules to see if the x stuff is on the top or on the bottom, and that will determine your answer. So this is just more of the intuitive way and the shortcut here. So here you'll notice that, okay, well, we have an x cubed term on the denominator. The 4 is there to make it a little bit bigger, but relative to everything, it doesn't really matter. I mean, it does in a way, but this grows so much faster than the top. The top is an x squared, the bottom has an x cubed, so this is still going to be bottom heavy. If you want to think of it as a balance, it's going to be bottom heavy, which means the denominator matters more, which means that that in the long run, in the perspective of infinity, the whole thing goes to 0. So these kinds of problems might actually seem kind of scary because it's a whole bunch of stuff, and you're thinking about, oh my goodness, like infinity. But these problems are actually not so bad. You're actually just, it's kind of cool because you're looking at things from a different perspective. From an infinity perspective, these things just fall away. They just go away, which is so cool. And you know, the thing is, I feel like math is that subject that all sciences rely on, but there aren't really that many cool demonstrations for math. Like for physics and astronomy, you get to zoom out. You get to zoom out and see galaxies and stars and space. So you get a different perspective. And then things fall away. Those little things become more and more negligible. But here, when we do limits, it's like that. When you increase your perspective, these little things fall away, and you only focus on the things that are left. So if somehow there was some beautiful demonstration of this, I think more people would love math more. It's just that you don't get to see cool images of space. But we can imagine this in our minds. We can imagine this in our minds. But in a way, the limits as x approaches infinity, you're thinking really just the big picture. We're not thinking of x approaching a specific value anymore. We now just want to know what the end behavior is. So as you might imagine, for negative infinity, you do the exact same thing here. You can follow the same logic all the way down to 1 over 4x. And even then, it's still 0. It's just that, you know, even if it's negative 1 over 4, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, that's still approaching 0. So the limit is 0, even from the left side, the negative side, right? Okay, so I will write this out rigorously. This is still more intuitive, and this is the shortcut for finding these limits, but I'll show you the long way because, you know, your teacher might ask you to do it initially when you're learning about limits, just to make sure you understand what's going on. But just in general, this works for any type of question. It's just that if you have something like this, and I'll just prove a point by exaggerating the coefficient a bit. Okay. Minus 5x as x approaches, let's do negative infinity this time. Like I said, the method is exactly the same. It's just when it comes to negative infinity, we have to be careful of the exponents, if it's even or odd, so if it's positive or negative, stuff like that. But when x is negative infinity, so really, 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 really negative, this 3 will fall away. Because even especially when you take it to the power 4, that's even. So that's going to be really, really, really big. This will fall away. This negative 5x will fall away. So we have our x to the 4th as our leading term for the numerator. And whatever this is, 100,000 x squared for the denominator. Now we just need to simplify this. So we have the limit of, as x approaches negative infinity, again with our exponent rules. So how does this simplify? X to the 4th divided by x squared gives you the x squared on the top, the numerator this time, because this cancels out, over 100,000. So now, since the x squared is on the top, as opposed to before I had 1 over 4x, this tells me that the top, which was x to the 4th, goes so much faster than this huge thing x squared. Now, just because this coefficient looks really big, 100,000, that seems really, really big, but that's still, even 100,000 times x squared still doesn't outpace or outweigh my x to the fourth. Why? Because we're looking at the context of x being negative infinity. Negative infinity. Infinity is not a number, but it being infinitely negative is so much larger than even 100,000. So we're scaling. The perspective is so huge. It's so zoomed out that even this coefficient doesn't matter. So as x gets really negative, because this exponent is even, we go to positive infinity. Positive infinity, because a negative number squared is positive. So in this case, it's positive infinity. Okay. And there you go. Positive infinity. Okay, so that's it. You do the same method for any type of numerator divided by denominator type question. So basically what we're doing is we're comparing the leading terms of the numerator with the leading terms of the denominator. Now if they happen to be the same, let's do an example where they're the same. So we did one where the bottom was heavier. Now the top is heavier. Okay. Now, if they are the same, it's exactly the same. It's exactly the same if they're the same. So the limit of 100x to the fifth minus 40x plus 2 divided by negative 5x to the fifth plus 7. Plus 8. How about that? Plus 8. How's this? Limit as x approaches infinity. Okay? Again, same thing. When x is really large, things just fall away. They just fall away, which is so fun. Crossing out, crossing out, crossing out. So we're thinking about the numerator and the denominator separately, right? So now we're doing just this, and this. So notice that we have x to the fifth on both the numerator and the denominator. So they're basically increasing at the same rate, which means they just cancel out. Which means this limit is just, what is this? Limit of 100 divided by negative 5. So you have a positive divided by negative. So just negative 20 of x approaches infinity. And we've already done limits of a constant function, right? So just negative 20. That's it. So basically you'll either get some kind of constant if they go at the same rate. You'll get an x or x squared or x something on the denominator, which makes the whole thing go to 0. Or you'll get something with an x squared, an x or an x squared or x cubed or something on the numerator, in which case if you're doing it, if the limit's to infinity, then the limit itself is infinity. Or if you're finding the limit when x approaches negative infinity, then you need to look at if that's even or odd in the exponent once you've simplified everything. That's it. So let me just quickly explain why we can do this little trick. I mean, it seems awfully hand-wavy to just be like, oh yeah, things cancel. It is super fun, but there is a little bit more rigorous of a way to show what we're doing. And it just really rests on one fact. So let's do this problem again with the long way, which might kind of come up. Your teacher might want you to do it this way initially when you're first learning about limits at infinity. So since we haven't actually directly talked about properties of limits, like pulling out a scalar, for example, or if you can add limits, those are just, it's basically everything you would think, but we just haven't directly mentioned it, so we can't assume it, but assuming that we kind of do know that, I'll explain the rest of here. So what I mean is, let's do this problem again, but just a little bit more rigorously than hand wavy. Hand wavy wavy. And then it'll give you an idea for what to do for the rest of the questions. But okay, so we're gonna do this problem again. But really all you need to know for these rational type functions, the main thing we really need to know is that the limit as of 1 over x to the power of anything, n, okay, where n is greater than 0, okay, and we'll deal with like square roots and stuff like that later, just because you do need to study other properties of certain functions. Unless you have a specific case, I'd love to take a look, but generally we are talking about polynomials divided by polynomials here. But if you know that the function's like strictly increasing and all that kind of stuff, you can kind of use the same logic. It's just there are a little bit more there are more conditions we have to kind of deal with. But in general here, let's talk about n being greater than 0, because if n equals 0, then this thing becomes 1, and then you have a constant function. So we're talking about positive numbers here. And so limit of this thing as x approaches infinity, and also limit as x approaches negative infinity, these both equal 0. Okay, so limit as x approaches negative infinity of 1 over x to the n. I didn't write it again, but you know what I mean, right? The limit for both of this thing for both infinity and negative infinity is 0. That is the only fact that we really need to know to do all these other limit problems here. It might not look like it, but let me show you what to do. So first thing, that's kind of what we're saying when n equals 1, the 1 over x. As x gets really, really, really big, you have 1 over something really, really, really big, and that would be 0, right? Same with the negative. It's just negative 1 over something, something, something really big would be negative 0.0000000000000000001, which is just approaching 1. So the limit is 0. So what we do to show this, just in terms of the getting rid of stuff, like getting rid of this -6 and the 7 and this, what we're really going to do is we're going to look at the highest power of x on the denominator. So there's a few ways to do this. We can just divide by the leading term itself, the 4x cubed, on the top and the bottom, but we can also just, the key part is the exponent of x. So we can divide by x cubed. Why do I want to do that? Because I want to directly apply this fact here. So I am going to divide by x cubed, which is the same as multiplying. So I'll write it like this: divide by x cubed on the top and the bottom. Okay, that's kind of a weird, wonky way of writing it. But remember, if we are, if we multiply by something on the top and the bottom, as long as it's the same thing, we're just multiplying by 1, which just gives us the original thing, so it doesn't change this at all. But we'll just end up rewriting this. So we have the limit, and if it helps you, instead of dividing by that, and remember this is parentheses, right? This needs to have parentheses, but instead of dividing, you can think of it as multiplying by 1 over, if it helps you to see the distributive property here. So essentially we'll be multiplying by 1 over x cubed on the top and on the bottom, like this, like so. Sorry, the birds are chirping. I love it, but I don't know if it bothers you. But what we do now is we just distribute. So the point of doing this is we look at the highest power. I should write that. Highest power of x in denominator. So we're just doing only in the denominator because we're essentially like normalizing everything. So we're just going to think of everything relative to the denominator just to get rid of it. So we're just going to sort of make this the unit, the 1, and then everything else kind of gets scaled down by that. So now we just distribute this thing by multiplying each part, okay, like this, and then just using our exponent rules. So now we have limit of, and now we can just write each part individually. So we have x squared over x cubed minus 6 over x cubed all over, so you do each part, all over 4x cubed over x cubed minus 2x over x cubed plus 7 over x cubed of x approaching infinity. Now, I did say this was more rigorous, so nobody says you have to do this all the time, but if you want to convince yourself that our reasoning of things falling away is actually true, this is where it really comes from. So now we're going to simplify everything, just, with our rules of exponents. So this becomes 1 over x, right? This is 6 over x cubed, that's good. This part cancels. The x cubed and the x cubed here cancel, so we just have the 4. This x cancels with this, so we have an x squared on the bottom. So I'm just going to rewrite that because that got messy. The limit x approaches infinity of 1 over, 1 over x minus 6 over x cubed over 4 minus 2 over x plus 7 over x cubed. Now the only other limit rule that we need to know that we haven't directly said is that you can essentially distribute this limit. And that kind of makes sense, right? The limit of this whole thing is if you're thinking x is really, really big, what is this approach, what is this approach, what is this approach, what is this approach? That is this approach. So other than that, assuming that is true, then now we can just apply this, and we can also pull out these scalars, okay? If we're really going to write every single thing out, I would write limit of 1 over x is x to infinity minus limit of 6 over x cubed as x approaches infinity. Then I'll pull out the 6 so that I have a 1 over x cubed so that I have this exact rule. So sometimes this rule is written as c, like some kind of constant, any constant, but this is the typical way, and that's like the actual important meat of it. So without writing all that, but hopefully you get the idea, we now know that 1 over x to the power of n, any n, so n equals 1 here, this goes to 0, this goes to 0 because the 1 over x cubed goes to 0, the 4 is still 4, this goes to 0, this goes to 0, everything goes to 0. So now we have 0, 0, 0 minus 0 is 0 over 4 minus 0 plus 0 is still 4. And this thing equals 0. That's it. That's actually what's going on. So why do we care about doing this? Like I said, we're dividing by the highest power of x in the denominator so that we can normalize this, so that we see if we get the x on the top or on the bottom or how it's all weighted. But it also tells us what things disappear. So when you distribute this part, as long as you're doing on the top and the bottom, everything stays balanced. But then you also see which terms become have this form. and then those all go to 0, and then you just see what is remaining. Sometimes you'll get 0, sometimes when you normalize it, you'll get some kind of x on the top, sometimes you'll get an actual constant number. But remember, anytime you have something over x, or a power of x, like a constant over a power of x, it becomes 0. So that's the actual reason. So we're not just canceling out the 6 and canceling out the 7 or canceling out this negative 2x. It's really when we're normalizing relative to this power. So I hope that this helps you with the intuition about this and what we were doing here when we were estimating things. Like I said, we can do like square roots and other types of limit problems, but for now, when we're doing the rational ones, we're really going to focus on just polynomials divided by polynomials for today, and then we can do other types of limits. But I just didn't want to introduce like needing to focus on whether or not a function is increasing, strictly increasing, or whatever, or decreasing, or what other things we need to know. So, but if you do have a question, like I said, you have a specific problem in school, let me know and I will take a peek at that. But next we will talk about cosine and sine, and maybe some like exponentials and exponential functions, and also, which actually are basically just like this. And then if you have any other questions, anyone who's watching this, if you have any other questions, I will make like a miscellaneous limit at infinity type video, and then we will go back and introduce limits properly with x approaching a specific value, and we can talk about different ways to evaluate that. But hopefully that covers everything that you need to know for now, and I hope that this was helpful. Let me know, and I will see you around. Bye bye.